All right. Hello, everybody. So, is this microphone carrying through? Good. Okay. So today, thank you for your answers to the question, by the way. One of the things I like hearing about that is that it appears that you're all being taught that mental health is something you have to take care of. And this might be a generational thing, but I was never actually informed of that. So it's good to see that you have a leg up on this, realizing that mental health is something you need to take care of. And at first glance, unrelated note, but you'll find out it's apropos by the end. The Nobel Prize in Economics was awarded yesterday, if folks follow these things. And it went to, oh, no, it wasn't me. Jeez. Yeah, thanks. Anyways, I appreciate a good sarcastic huzzah. But all that said, it went to three economists, David Card, Josh Angrist, and Guido Imbens. And the contribution that they cited for was what's called the credibility revolution. For folks who follow the New York Times, Paul Krugman has a nice discussion about it in his column today. Now, the credibility revolution that's what it was termed in economics. In political science and public health, which is more of where I'm coming from, it's called design-based inference. And that was all of the causal material we did in the first 4 or 5 weeks. A lot of that, in terms of the initial studies, relates back to the three scholars who were cited. If you'll notice, David Card was cited for the Card and Kruger, New Jersey, Pennsylvania distinction. And a lot of the work we're doing in here flows from the credibility revolution. It's not simply statistics, is this significant? But if you find this effect, can we actually say that this intervention or manipulation will lead to some change? It raised the bar across fields, quite a bit in economics, certainly in political science, certainly in sociology, certainly in public health. It raised the bar of statistical analysis from correlation to causation. And you can't always hit that causal bar, and we talk about that here regularly, but it sort of raised what entire fields' expectations were from a quantitative study. Not just, hey, look, these two things move together, or I can model this enough to get rid of potential confounders, but actually, here's a natural experiment. Here's a field experiment. Here's some manipulation that occurred, and I can trace this manipulation causally back through to an outcome of interest. As a follow-up to this, and tying into today's question, there was a fourth scholar whose name was omitted. Alan Kruger was an economist here. He was chair of the Council of Economic Advisors. Like the economics department here is obviously first-ish, right? There's like us and Harvard and MIT, they're always sort of, but it depends on the measure. And amongst economists, he was up towards the top. I'd say I knew him, but actually I met him a couple times and he would have no reason to remember me. But he ended up, in important ways, winning the game that I've spent a large part of my life playing, right? Famous professor, full professor, policy impact on students, impact on mentors, all these sorts of things, right? About 2 years ago, his family came into his office and found him dead of his own hand, which is why he was not cited, but it was clear that he was part of this group. I bring this up in terms of the mental health today, and I was happy to see this appears to be generational, and I'm pleased to see this. You are aware that mental health is something you need to take care of. So I was very happy to see what was written up here. And if it might not be today, it might not be tomorrow, but there might be a time where you need to know this or hear this. You are more important than your achievements. You are more important than your accomplishments, and you are more important than your failures. And there might be a time where you need to reflect back and just realize that there's more people that love you and want to see you alive than you will ever realize. So if it's not today, store that somewhere, because it's possible to achieve just the utmost levels of achievement. It's just to hit top levels in your field and still have a hole and an emptiness in you that could drive you to do things that hurt yourself and lots of other people. So just realize, yeah, I'm kind of petering off here, but just realize that there's people who love you, who want to see you alive, and you're more than your achievements. Okay. So I don't know how to transition from that to regression. So we're just gonna like do it. Precept this week, canceled. It'll be back next Monday. Yeah, back next Monday. More applause today. Data camp, if you go on data camp, there's a sign, it tells you when the assignments due exactly by time. We're gonna stick with that. Just log on to data camp. You should have a login. I think about 60 people have finished it, about 100 haven't. So just go do the first course by the end of this week, the second course by the end of the last week. And if you find yourself liking it, please continue with it. Okay, it's a great way to gather skills. Along those lines as well, in future semesters, if you find yourself loving it or just appreciating or enjoying it, I always get 10 or 20 extra free subscriptions because I teach one course that uses it every semester. So if you want a subscription next semester, just send me an email and I'll add you to that class. Okay, so as long as I'm here and doing this, I'm happy to share subscriptions with people who are using it, and this is open to grad students as well. Let's see, quizzes coming back Thursday, problem sets were back Thursday. Please submit regrades via the Google form. And oh, also, I noticed that the preceptors have been putting in a lot of work, and I see it. Every year, I'm just blessed with great preceptors, and I really do go out of my way to pick them. Applause. Extra office hours, getting things back promptly, grading accurately. All those things are happening, so thank them. And just a shout out, if you didn't see the note for Jacob, was that a public invitation for your office hours?
It is, yeah.
A mental health office hours where, do you want to just shout out what you're doing?
Sure. Yeah, tomorrow morning my office hours tend to do, I think you're all set with intern. I have an adorable border collie puppy. If you want to just say hi to the border collie puppy.
Okay, cool. All right. So today, we're going to conclude the first discussion of the regression. The first discussion we're going to have of the regression is simply putting a line to data and staring at it. We'll revisit regression after we build out tools of statistical inference, which we haven't done yet. But this is purely a descriptive tool. The first paper we're going to talk about it's a really fascinating design. And the question that the author asks is, who follows whom? The title of the book is Follow the Leader. And the question that the author wanted to get at was, do politicians follow public opinion or shape public opinion? All right. So to what extent do I have policy beliefs when I report on surveys? To what extent do I have policy beliefs because that's what my preferred politicians say? To what extent do those politicians have beliefs because they listen to their constituents? And you see the obvious design problem, I hope, in backing out any hope of causality here, because they're obviously co-causing each other. No one thinks that politicians run around calibrating exclusively to what their constituents say. And everyone realizes that voters, here in the US, but I'd hazard over the world, take policy cues from the politicians they prefer. If you're a prime minister, president, legislator of some form says, I think policy X is great, a certain proportion of the population is going to follow along. Okay. So what we're going to do is look at how we can use a regression analysis to disentangle that and in what scenario. The less than scholarly link, by the way, don't do it now, but I think it was a Jimmy Kimmel bit from about 5 years ago, where he was asking people what they thought of Obamacare and then what they thought of the Affordable Care Act. Right? Well, you don't like Obamacare, but let's look at the Affordable Care Act, and everyone seemed to like it. And there's those sorts of things. I mean, it was a cheap and easy target. It's Jimmy Kimmel, but it kind of conveys the point we're trying to get at. Okay, let me flip this up to a full screen for you. So to understand the design, I want to distinguish between two different data types. The first type, and we talked about this, but I just want to get this point home. There's two classes of data, two data types that we see regularly. One is cross-sectional data. And this is where you observe data, all observations once and only once. Most of the analyses you're going to do in this class follow from here, okay? The second type of data set that we're going to encounter is panel data. And have you done the Reinhardt and Rogoff inflation and GDP precept assignment? That was panel data because it was the same countries over time, all right? The panel data analyses involve a little bit more nuance than cross-sectional data. So if you find yourself interested in that, it's something that statisticians, econometricians, political scientists, and sociologists have been chewing over for about 40 or 50 years. So it's pretty well established. 346, I believe, goes into more detail than I will in that field, okay? But the idea with cross-sectional data is you have a snapshot once in time. Panel data allows comparisons on the same observations over time. And in that case, we can start to see how things change. So for this particular study, let me just make sure it's the next slide. I hope I have the order right. Yep, okay. Let me tell you a story about this wondrous period called the late 1990s. It wasn't even this millennium. The economy was booming. The Matrix came out. People frosted the tips of their hair. Does anyone still do that? Yeah? And oh, as an aside, are mullets cool or not? Can I just get a show of hands? Because I'm having this argument with my wife. It's an 8-year argument. Show of hands for yes? Show of hands for no. Okay, so it's split. Fine. Kim Jong-un actually made them illegal in North Korea. Do with that what you will. But this was late 1990s, and our federal government was running a budget surplus. After the Clinton tax increases of 1993 or 4, followed by a booming economy driven by internet websites that had no business being valued as highly as they were, but they were, our government was taking in more money than it was spending. We had a budgetary surplus. And one of the questions that we faced as a country is, what do we do with this? You all know how this plays out. But there were real concerns, right? Like, what happens if we spend our debt down to zero, and how do we handle this money? One of the questions that came out in the 2000 race, which was George W. Bush versus Al Gore, governor of Texas versus the vice president at the time, was what do we do with Social Security? Okay? For those of you who are American citizens, in 40 years, you'll start caring about this a lot more. For those of you with aging parents, that you might be caring about it now. All right? And George W. Bush's proposal was to privatize Social Security. He looked at this massive amount of money that was dedicated to Social Security and said, let's put it in Wall Street. Let's put it in the stock market and let her rip. Look at the gains that Wall Street can give us. This was called privatizing Social Security. Al Gore wanted to put it in what he referred to as a lockbox. Right? These are government bonds, that they're backed by government bonds that the government has brought from itself. Back in the early 1980s, Alan Greenspan led a commission that sort of set aside money for Social Security for the boomer generation, okay? So there were some savings sitting there. And he said, we're just gonna put it in a lockbox and not touch it. This issue was a driving concern of the 2000 race. Basically, what to do with our nation's pension program. The author, Gabriel Lenz, of this study, wanted to get at whether or not people changed their minds about whether or not to privatize Social Security after it became a campaign issue. Does that make sense? Before it was a campaign issue, no one really cared. Afterwards, everybody cared, and we want to disentangle this. So the approach that he took was the following. He found survey data before and after it became an issue, before this became an issue in the campaign. So before it was an issue, people had opinions. After it had an issue, became an issue, people had opinions. And he compared the two slopes on those lines. So let me show you what's happening in these figures. On this scale, the x-axis is support for Gore versus on the left versus support for Bush. Roughly, that's Democrats to the left, Republicans to the right, but it's a multi-point scale, okay? Then, what he wanted to know was what we thought should happen to Social Security. And that's what the line is telling us. So before people knew the party's opinions on this, if you look at the left-hand side, the slope is 0.22, it looks relatively flat. So before it became a campaign issue, regardless of your support for either candidate, there was no real relationship between your support, which candidate you supported, and what you thought of privatizing Social Security. The right-hand panel shows you the change. On the right-hand side, what he finds is that after George W. Bush looked at the stock market and said, oh my God, let's give it all of this money and then we can I'll make you all rich when you're retired. And Al Gore was like, nope, conservative investment strategy, this is people's pensions, put it in a lockbox, don't touch it. It became an issue at several presidential debates, campaign ads, interest groups, the whole thing. And take a look on the right-hand side, what happens? Folks who supported Bush all of a sudden want to privatize, and those who supported Gore don't. So in this work, this is an example of what he calls following the leader. The candidates staked out policy proposals, and voters aligned with the staked out policy proposal of their preferred candidate. People didn't care about this issue until candidates made it an issue, then they sorted along it. The issue itself was not reflecting underlying exogenous preference that could be measured prior to the politicians taking a claim on it. The point for this course that I want to get at, and we can talk later about whether it's statistically significant, it is, but just eyeball it, there's an effect there. Is that by comparing regression lines before and after an event, we can get a sense of how that event affected the relationship between two variables. So simply by drawing lines and putting lines to data, we can start to find how interventions and changes can lead to some outcome. Okay, and how that can change over time. There's fancier statistical ways to do this, but honestly, this figure conveys the point much more clearly than a high-end econometric model would, okay? And this is the sort of analysis where you can use regression comparisons. You can compare regression lines across different groups or across the same group in different times when there's some intervention in the middle. And that's the design I wanted us to get across here. The next idea we're going to talk about, oh boy, regression to the mean. This lecture is going to be filled with topics. The origin of the regression line, it goes back to a mid to late 19th century British polymath named Francis Galton. Okay, and he was at the head of a whole variety of different fields in his day. And he actually he's the person who coined the phrase standard deviation, regression, and eugenics. Yeah, right? The reason for that, and you need to understand late 19th century British, and none of this is excusing any of this, by the way, I'm just drawing the intellectual connection, and it's garish. It's horrible. These were people interested, these were upper class, white, educated British people, and this carried through into the 20th century, who studied and were interested in agricultural experiments and animal husbandry and decided to bring all that over to people. So there's a dubious intellectual heritage to a lot of these things. One of actually, the most famous statistician of the 20th century was Ronald Fisher, who developed what we now think of as statistical machinery through a series of 3 papers in the 1920s. 2 of the 3 papers were published in the Journal of Eugenics. They've since been republished in less offensive named journals, but there's something of a horrible history here. Okay, that, and he was also one of the greatest geneticists of the 20th century. He also didn't think that smoking caused cancer. And anyways, there's reasons he's not a household name. In terms of intellectual accomplishment, he laid a lot of the groundwork we're looking at. So Francis Galton's paper on regression to the mean, going back to heritable traits, okay? Let's start with this. Does anyone have a friend with two particularly tall parents? Just, can you think of someone? Yeah? Is their child tall but shorter than them? Can I get a show of hands for, okay, so who has friends with two tall parents? Okay, and then leave your hands up if the children are shorter than their parents but still tall. Okay, let's do it the other way. Who has friends with particularly short parents? Show of hands, okay. Of those, are their children still short but taller than their parents? That one got a pretty solid majority, okay? This was the insight in Galton's paper, that tall parents will have children that are, two tall parents will have children that are tall but not quite as tall as their parents. Short parents will have children that are short but taller than their parents. So the children of two tall parents will be a little bit shorter, and the parents of two short parents will be a little bit taller, and that's what he meant by regression to the mean. Sometimes referred to it as regression to mediocrity. Why is this happening? And it's a general phenomenon that we're going to talk about that I want you to understand so that you can keep your eyes open for analyses that make this mistake. And they do pop up. So in the case of height, some portion of your height is heritable. It comes from your parents. Some part of your height is purely chance, right? You ate things, you did sport, whatever, what have you. But just the random chance of genetics in your life is the other part. So let's take people with two really tall parents. The parents are actually tall because of a heritable component, but also because that random component swung in their direction. Does that make sense? Now let's think about their kids. Their kids get the heritable component, but the random component, which was high for their kids, is likely to be high for them, is likely to be smaller for their kids. Right? The random component is most likely to bounce back. Running through the logic again with short parents. Let's imagine you have two parents that are very, very short. The reason they're short is partially genetic and what we're calling in statistical models systematic. And then part of their shortness is just random. The way, diet, whatever, what have you. So their shortness is the heritable part, but then a random part that bounced down. When they have children, they inherit the heritable part, but the random part, which was uncommonly low, is likely to bounce back up in the next generation. Do folks see the logic to this a little bit? It's a tricky subject, but it does befall common analyses. Mistaking regression to the mean for a systematic relationship in the data is called the regression fallacy. Let me give you an example of this. This comes from, while we're doing Nobels today, Daniel Kahneman, who's, he's still in SPIA, right? See? Okay, I believe he's still in SPIA. Won the Nobel about 10 years ago for his work in behavioral economics, him with Tversky. And they give this example from one of their famous books on the Israeli, it comes from the Israeli Air Force. And what happened in this particular example is the Israeli Air Force was interested in having people land planes on, is it battleships? They wanted people to land planes on battleships properly, right? You obviously don't want to do that poorly because if you make a mistake, it's expensive. I'm not sure if anyone's ever dented their parents' car. It's like that, but like with an airplane. So what they did, they wanted to know the answer to the following question. If someone does a great job, should we reward them? Or if someone does a really poor job, should we punish them? And this is the question they asked. What's the best way to incentivize good flight maneuvers? And what they noticed is when they rewarded people who did a really good job, they didn't do as well next time. And when they punished people who did a really bad job, they did better next time. Does it follow from that observation that the Israeli Air Force should be punishing people and not rewarding them for this behavior? At first glance, it seems to, but what we're encountering is actually a regression fallacy. The reason someone did a particularly good job landing was because they're a good pilot, but also things sort of fell their way. The next time through, we expect them to do well because they're a good pilot, but not as well because things might not fall their way. That chance error won't fall in their favor. If someone does really, really poorly, then it's because they're not a great pilot, but also things went against them just by chance. In the next round, we expect them to do poorly, but things are going to fall in your favor a little bit more. So you're likely to do better. And that's a regression fallacy. It has nothing to do with the systematic component. It has to do with how things fall. What's a proper way to test this? You don't reward people who did well and punish people who did poorly. What you do is you take your sample and before it's run, you reward half the people and discourage the other half, and then look and see how that affects the next time. There's no randomization happening in this analysis, right? You're conditioning on something that was random, how well you do, and it leads to the incorrect inference. If you ever see an analysis that comes back that feels like this, really great people do a little bit worse next time after something happens, and really, really people on the low end do a better job the next time because of some analogy, because of some intervention, then keep your eyes open and look for a regression fallacy. This does show up occasionally in published studies, and just be aware that this is something that it's an error of inference. Okay. We're winding down on the regression for a little bit, and we're going to go a little bit into probability and inference. And we're going to focus on probability and inference. Well, we'll get to that question in just a moment. We're going to focus on probability and inference on a single question. We're going to build up to an answer to a single question. Given the outcome in two different groups, can I say the difference between the groups is likely systematic? We'll formalize that, but we're going to take a sidebar for a few weeks, build out that question, and then turn around and apply it all to the regression again. Okay? So we're going to focus on a very, very simple model. And the first step of this is understanding the difference between modeling and inference. In this case, I call it the data generation process and inference. So we just need a little bit of language. What we're going to assume that on the left-hand side are a series of population level parameters or variables that we never see, but we'd like to see. On the right-hand side are data that we see. So the question of inference is, how do we go from data that we see to population level inference that we don't see? To put it differently, let's say I wanted to run a survey on Phil Murphy's popularity in the state of New Jersey. He's the governor, right? There is a number that captures that if I ask right now. If I were to ask everybody in New Jersey, and they were all to reply honestly at the exact same moment, that would be a number, right? I'll just never see it. What we could do is run a survey over a day or two, have a couple thousand people reply, and then the question is, how do we take that sample, that data that we observe, and relate it back to the true thing we care about? So in this case, the true thing we care about is called the parameter. The parameter is what we would like to know. It's the answer to our question. What is the relationship between these two variables? It's a parameter. What's the effect of a 1 unit move in this on that? It's a parameter. What's the mean of this? Again, these are parameters. This is what we want to know. What we actually observe are statistics. A statistic, the formal definition is a statistic is any function of the data. So we're going to focus on the statistic, the standard error, and the sample mean. But really, the statistic could be the median. It could be the fifth observation. Any function of your data is a statistic. The question of statistical modeling is going from the left-hand side to the right-hand side. How do I write a model in terms of parameters that I believe is generating my data? Or is at least representative of my data? Going from right to left is the question of inference. How do I take my data and make claims about how close the estimate is to the truth? And those claims are necessarily probabilistic. I don't know how close my estimate is to the truth without knowing the truth. But we'll build out some methods that will allow us to say, you know what? There's a pretty good chance that this is about how far, that there's a pretty good chance that this confidence interval will contain the true value. Okay, so it's going to be, the left-hand side says, here's how we're going to construct our model that represents our data. It's in terms of population parameters. The right-hand side is, given my data, how do I construct statistics that let me go back the other way? Okay. So the big difference, and I encourage folks, if you develop a taste for this in this course, obviously continue 346. As well, as you go further, you're going to find you need more probability theory. We've more or less taken it out of this course with the understanding that if you're interested in it, the ORF sequence is excellent. And this might be a year or two down the line. But if you find yourself learning this material, at some point, you're going to hit a ceiling. Okay? We're just going to go through some of the basic ideas right now. A random variable assigns a number to an event. There's fancier mathematical ways to say this, but that's what a random variable is. A couple different examples. If you flip a coin and you get heads, you return a 1. Otherwise, you return a 0. If you're gambling, if you win, you get $100, and if you lose $10. If you vote, it's a 1 if you vote, a 0 if you don't vote. We can use it in survey responses, but it just maps some event to a number that we can write down. Okay. One of my colleagues defined a random variable as anything you can bet on. Okay, I don't go that way. But it takes some event and maps it to a number. We're going to discuss 2 different types of probability distributions in here. And this chart, this next slide is mostly for reference, to be completely honest. We're not going to walk through every line, but there's times where bits of this slide are going to come back and I'll bring them in when they do. I just wanted it up here on one page for you. There's 2 types of probability distributions that I'm going to expect you to understand conceptually. The first is what's called a discrete random variable, which just means it takes on values at a discrete number of points, and we're going to use a binomial random variable to represent that. A binomial random variable is, if I flip n coins, what's the probability of getting p heads? And that's what that notation means. So if you'll notice, it's a discrete event. We're going to flip 5 coins. What's the probability of getting 3 heads? All right. There's some math of this that R will do for you, so we're not going to go too far down that rabbit hole. In the binomial distribution, there are two parameters. The number of coin flips, and P is the probability of success on a single coin flip. Okay? So if I flip 10 coins and they're fair coins, then if I were to say, well, if I want to think through this number of heads that I get from that, I'm going to model it as a binomial random variable, 10, 0.5. And that's going to give us a way of modeling outcomes that are discrete. The expected values and the standard deviations, I just want to leave those up. We'll circle back to those when we need them. I just put them up here as a reference for right now. The second random variable we're going to talk about are normal random variables, sometimes called Gaussian random variables. And these are just bell curves. The normal random variable is a continuous random variable. So the first distinction you need is between a discrete random variable that takes on values 1, 2, 3, 4, 5, or 0 up to some number, and a continuous random variable that can take on a value over a continuous range. There's lots of different distributions, but we're just going to focus on the binomial and the normal, because those two will give us the basic insights we need to model a wide array of different outcomes. So the normal random variable has two different parameters, mu and sigma squared. Mu is the mean. Sigma squared is the variance. Sigma is the standard deviation. Sigma squared is the variance. Mu governs where the peak of the bell curve is. Where's the center? Sigma squared governs how much it spreads out around the center. As half an aside, one of the joys of studying statistics, I'm very much encouraging you to, giving you this as an idea to, encouraging you to take courses beyond this one, is in my honeymoon in Athens, we were in Athens for a few weeks as part of our honeymoon, and I could read street signs. You learn all the different Greek letters as part of this, so like the spillover effects in your life are boundless. So mu is for the mean, sigma squared is the standard deviation. And let's go through this. We'll refer to a standard normal distribution as that bell curve up there, which is mean 0. If you'll notice, mu is 0, it's centered right on the y-axis, and the variance is 1. If I talk about a standard normal distribution, that's what it is. All right? The formula for that curve, and that's called a density curve, and we'll go into density curves, but the formula for that curve is 1 over square root of 2 pi e to the negative x squared over 2. All right? As an aside, I was weighing whether or not to do this, but I think we'll just give it a shot. An open extra credit question due before Dean's Date if you can, worth 1 point on your total grade, is if you can show me that f of x integrates to 1, that's 1 extra credit point. I'll warn you, because you can turn around and Google it and get the answer. It's in Stack Exchange. I'm going to push you past that. All right? Okay. So what the standard normal is conveying and what this density curve is conveying is that if we were to look at the data that comes from a standard normal distribution, it would mostly fall towards the middle and not too much in the extremes. That's sort of the first takeaway. The second takeaway is the fact that the density is symmetric, which means we're just as likely to see positive data as negative data. So qualitatively, the two things to know about the normal distribution is that most of the data clusters around the mean, and it's symmetric, so we're just as likely to be above the mean as below the mean. Another way to say that is the mean and the median are the same in this particular distribution. The area under the curve adds up to 1. And in this curve, about 68% of the data will fall within plus or minus 1. And about 95% will fall within plus or minus 2. So when we push this out a little bit and talk about 2 standard deviations, that's where this is going to come from. But that's sort of foreshadowing. Oh, here's a figure that shows the standard normal distribution under different means and variances. The standard normal, again, is in black. That's a mean of 0 and a standard deviation of 1. If I change the mean to 1 and the standard deviation to 1, you see how it just shifts over but keeps the same shape? That mu term is going to govern where the center of it is. The second parameter is that sigma term that's going to govern the spread. So if I keep mu at 1, this is the blue line, and I change sigma from 1 to 2, it's just going to spread out further. It's still going to integrate to 1. There's still an area of 1 under that curve, but it's just spread out a little bit further. And those are the 2 parameters that we have in the normal distribution that govern the entire curve. So one of the things we'll need to do is convert random variables to probabilities. There are 2 aspects of a random variable, 2 functions related to every random variable that we'll talk about. The first is the probability density function, and the second is the probability distribution function. So the density function asks the following question: how likely does x take a particular value? So when we go back to the normal curve, when I say that most of the data is likely to appear underneath towards the middle, that's because the density is highest there. The density tells us where over the range of values are we more likely to see outcomes. The second part is the cumulative distribution function, or the probability distribution function, that says what's the probability of seeing a value below a given number. So this is what we'll do to ask, well, what's the probability of seeing a number 3 or below? A little abstract. We're going to come back and work through this in applied examples and details over the next week or 2. Let's see. Over the years of teaching this course, I've progressively pulled out the actual pencil and paper mathematics year by year by year. So this slide is actually a little bit vestigial, where I'd actually give you like actual problem sets and things, and I'm leaving it there just out of fondness for problem sets. But no one gave applause for fondness for problem sets. Like pencil and paper probability questions, does anyone? No, yeah. Even the sarcasm was half-hearted on that one. That's okay. It really, really is. We've built up other parts of the course in response. Okay. So the question we're going to ask, and here's the key idea that we're going to talk about, which it's called, we'll talk about it a little bit. I'll introduce it formally on the next slide. But there's something called the law of large numbers that says as we get more and more data, the average approaches the true value. It's a nice mathematical tool that justifies getting more data. And sometimes in social science work, if you get a weird result, the answer is go get more data and test it. And it's the law of large numbers formally as a mathematical construct that allows us to argue that this is what we should do. So this comes from a paper in the Journal of Theoretical Biology. For folks who go into theoretical biology, some of the arguments there are beset by the same problems as social psychology, where the argument isn't all that the mechanism isn't all that well thought out. But what people will say is, oh, look, here's an observed pattern in the data. Let me go back and reverse engineer evolutionary incentives that led us to it. Does that make sense? And that's the sort of that's the sort of argument that leads to false positives. What we want to do is hypothesize a mechanism and go the other way. So in the mid-2000s, a string of papers came out. Big and tall parents have more sons. Engineers have more sons, nurses have more daughters. Violent men have more sons, and beautiful parents have more daughters. Now, any one of those, you could sort of, if I were to ask you, create a story of an evolutionary story that's consistent with any one of those headlines, you could, right? Or you should be able to, just talk about it over dinner and you can come up with it. The question though is this what's really happening in the data? No one doubts that the authors in those studies went through, gathered data, and found a significant result. The question though, is the result actually there? So in order to test the last one, where beautiful parents have more daughters, okay? Andrew Gelman and Weeklam, one of his co-authors, went through and they did the following. They said, they looked at the result and said, I just don't buy it. I don't buy that beautiful people have more daughters. So what they did was they said, this was done off one data set, let's just go gather more data. And what they ended up doing was they went back to people's most beautiful list, right? from 1995 to 2000, then they took everyone on time, people's most beautiful people and just measured how many daughters and sons they had. Right, so we're going to take beautiful people and just measure how many sons and daughters they have and tabulate it. They hired some research assistants to do this. After they did the 1995 data, the research assistants came back and said, 57% of the kids are daughters. And the authors were like, oh my God, this might be true. Then in 1996, they did it again and the answer was 56.6. And they're like, oh my God, really? Is my understanding of genetics in the world that far off? Then after 1997, it dropped down to 51.8 and they were like, thought so. And then they did it year after year after year, and they got exactly 50%. Exactly 50% of the daughters, exactly 50% of children over this 5-year period were daughters. If they get rid of duplicates, which is actually like, I guess like George Clooney showed up all the time or something. If they drop duplicates, it drops down to 47.7, where there are actually more sons. And in the population frequency, it's 48.5% of 48.5% are women. The point of this is that if you get a weird result, don't run off and start declaring it. You probably need more data to convince. And if you get more data, the law of large numbers that says that the sample mean gets closer to the true mean will make the effect disappear. One more example of this, I'll set it up now. This study came out in the National Academy of Sciences a few years ago. And the authors went through and they counted fatalities from hurricanes that had female names versus hurricanes that had male names. So they wanted to compare hurricanes and hemicanes. Their words. Now, we'll go into this study in just a moment. But like part of the reason you'll notice in here, I talk about gender and race a lot in here, not because George Soros calls me every year and he's like, Mark, can you go ahead and spread the gospel of critical race or whatever, right? No. The reason I use these examples is because they're really there. They're the easiest teaching examples. It's stuff that as fundamentally as an empiricist, I go, this is just happening. Study after study after study. All well-done studies find this is just a result over and over and over again. I'm pulling this up as one of the cases where it didn't seem plausible. The idea, the question here, oh, it's 2:20. We'll resume with hurricanes and hemicanes in a bit.